US Physics Olympiad, year 2022, USAPHO. Final round. Problem A2. A droplet of liquid metal has a constant mass density and constant surface tension sigma, which causes it to form into a sphere of radius r. Throughout this problem you may neglect gravity. A thin wire is inserted into the droplet and connected to an electric current source which slowly charges the droplet. There is a critical value of the charge Q0 that causes the droplet to split in half. Each half takes half the total charge Q0 over 2 and half the mass of the original droplet. The eject half is repelled far away from the other half, which remains in contact with the wire. Question A. For simplicity, assume the droplet splits as soon as the final state, after the droplet has split in half and the two halves are well separated, has a lower total energy than that of the initial single droplet. What is the value of Q0? Give your answer in terms of a dimensionless constant A multiplied by a product of powers of sigma r and the vacuum permittivity epsilon 0, and give the numeric value of A to three significant figures. Question B. As more charge is added to the droplet by the current source, it continues to split in half repeatedly. What is the charge Qn of the nth ejected droplet? Give your answer in terms of Q0. Question C. In the limit where all of the initial mass of the droplet has been ejected, what is the total work done by current source? Give your answer in terms of a dimensionless constant B multiplied by a product of powers of sigma r and epsilon 0, and give the numeric value of B to three significant figures. Solution for question A. For simplicity, assume the droplet splits as soon as the final state, after the droplet has split in half and the two halves are well separated, has a lower total energy than that of the initial single droplet. What is the value for Q0? Give your answer in terms of any dimensionless constant A multiplied by a product of powers of sigma r and the vacuum permittivity epsilon 0, and give the numeric value of A to three significant figures. Solution. From dimensional analysis we can find that Q equal to constant A multiplied by square root from epsilon 0 sigma r cube. To find the value of A, note that a droplet of radius r has a surface energy 4 pi r square sigma, and an electrostatic energy is Q0 square over 2c, where c is 4 pi epsilon 0 r, is the capacitance of a conducting sphere relative to infinity. Thus, total energy of the drop is this one, the sum of these two energies. When the droplet splits, the new halves both have charge Q0 over 2 and the radius r over 2 power 1/3, since the total volume stays the same. The total energy of each of the halves is thus this one. Setting E equal to E1 and solving for Q0, this equation, we will have this equality, which can give us a solution for Q0, which we got from dimensional analysis. and constant A equal this expression, which is approximately 14.9. This model is of instability of a charged liquid drop is not exactly accurate, and was chosen to keep the problem simple. In reality, it isn't enough for the final state to have lower energy. The repulsive electrostatic force needs to exceed the surface tension force, or else the bubble can't get to this state of lower energy. So in this case we can give you more accurate solution. We already counted that total energy is this expression, which consists of surface tension energy and electrostatic energy. First one creates inward force and the second one outward force. So when we add an additional Q0, we can increase force from electrostatic, which can prevail the surface tension force. To find what is point of instability, we can just take this energy and take first derivative by R from this energy and equalize it to 0. That will give us equation this one, and from here we can find that Q0 equal 8 pi square root from epsilon 0 sigma R cube, and the constant A equal 8 pi, which is approximately twice greater than in previous solution. Another way to solve this problem is not energy but force approach. We know that the electrostatic field just near the surface of this droplet from outside equal Q0 over 4 pi epsilon 0 R square. This field created by small area delta S and the rest of this droplet surface. We know that electrostatic field due to Gauss law, the difference between electrostatic fields from both sides equals exactly to this expression. So it means that because inside of this droplet we have electrostatic field is 0, so it means that total electrostatic field from rest of this droplet equal to half of this expression. And now we can count what is force delta F1 acting on a small charge delta Q on small plate area delta S. That will be this expression. And now to find what is pressure created by this electrostatic field, we can just divide this force by delta S, which will give us pressure P1 equal Q0 square over 32 pi square R power 4. And this pressure pointing outside. Now let's count what is the pressure due to surface tension, which is pointing inside of this droplet. We know that total force acting on a line of length L equal L multiplied by sigma, coefficient of surface tension. And if we take a small circle radius small r on this droplet, we can count what is the force acting on this surface inward, because for small radius r of this surface it takes volume angle which has regular angle 2 delta alpha, and the total force equal circumference of this area, which is 2 pi r multiplied by sigma, and we have to multiply it by sine delta alpha, which for small delta alpha just equal delta alpha. And now to find what is the inward pressure, we need to divide it by pi r square. That will give us 2 sigma delta alpha over r. But taking in account that small r equal radius of droplet r multiplied by delta alpha, finally we will get P2, pressure from surface tension, equal 2 sigma over r. Now we have to equalize these two pressures to find the critical Q0, after increasing which we will get electrostatic pressure will prevail surface tension pressure. Equalizing these two expressions, we will get same answer as for energy approach. So Q0 again equal 8 pi multiplied by square root from epsilon 0 sigma r cube, which is correct answer. Now we presented all three approaches for this question. Solution for question B. As more charge is added to the droplet by the current source, it continues to split in half repeatedly. What is the charge Qn on the nth injected droplet? Give your answer in terms of Q0. Solution. Consider the situation just before the number n split. At this point, the initial droplet has split in half n minus 1 times, so it has a volume that is 2 power n minus 1 times smaller than the original volume, and thus the radius is r divided by 2 power n minus 1 divided by 3. By part A, the charge required to split this drop is Qn equal Q0 over 2 power n minus 1 over 2. Once the split happens, the number n injected droplet takes half of this charge. So Qn equal Q0 over 2 power n plus 1 over 2. Also note that the radius of this droplet is r over 2 power n over 3. So that was solution for question B. Solution for question C. In the limit where all of the initial mass of the droplet has been ejected, what is the total work done by the current source? Give your answer in terms of a dimensionless constant B multiplied by a product of powers of sigma r and epsilon 0, and give the numeric value of B to 3 significant figures. Solution for question C. By dimensional analysis, the total work W done by the voltage source must be B multiplied by sigma r square. The work W is equal to the difference between the energy EF of the final state, where there are many small droplets that have been dispersed too far away, and the energy EI equal 4 pi sigma r square of the initial uncharged droplet due to surface tension. The final energy includes the surface tension and the electrostatic energy of all the small droplets which have a radius Rn and the charge Qn found in the previous problem. This means that the final energy is this one. Using results from part B, we can rewrite this sum as, putting all numbers from part B, we will get this total final energy, and to find what is work, we need to subtract from this initial energy 4 pi sigma r square. And finally coefficient B will be this one, which depends from constant A 14.9, which was given in first approximation, or 8 pi, which was counted in more precise estimation. So that was solution for question C. Now let's do more correct way to solve this problem. The suggested before was that we have to count what is potential energy for drops which were far away, but in that case we didn't count what was the kinetic energy which was produced during electrostatic interaction between droplets. We could suggest that one remaining droplet is not moving. In that case, all kinetic energy was received by moving away droplets. So in that case we don't need to count what is the initial potential energy of initial not charged droplet. it was 4 pi r square sigma, because we just need to count remaining energies for droplet. Let's do this. First, droplet was charged from 0 to charge Q0, so that was initially given energy. And after that we can just count what is the energy difference between start to divide droplet and the energy of remaining droplet. Let's do this. So energy of the initial droplet just before division was 4 pi sigma r square plus Q0 square over 8 pi epsilon 0 r, where Q0 was A multiplied by square root from sigma epsilon 0 r cube. Now, after division, the left droplet was with the energy E1, where we use a new radius R1 and new charge Q1. New radius was R over 2 power 1/3, and Q1 was Q0 over 2, and E1 in that case was this one. Now we can count what is the energy difference between initial energy E and the remaining energy E1. This is what we really need. And now let's do recursion. We have delta En equal this expression, and finally we just need to summarize all this delta E by N. That will be all this sum. And we see that this all going to sum of geometric progressions, which finally give us this result. Now we need to add initial energy given to initial droplet. So that was Q0 square over 8 pi epsilon 0 r. When we add them and also refresh that Q0 was this expression, A multiplied by square root from sigma epsilon 0 r cube, and also we counted that A was 8 pi. And the last step, we have to subtract initial surface tension energy 4 pi sigma r square. In that case, total energy which was receiving from current source was this one, and the coefficient beta was 4 pi multiplied by 2 power 8 over 3 plus 2 power 2 over 3 minus 2. That was correct solution for question C.